Hi, you are on Drop Table channel, and today we are going to talk about the most secret API in JavaScript that you or probably no one in your team doesn't know, and today I will reveal this secret. But first, please subscribe. I will wait here until you subscribe to my channel. Boop, boop, boom. Doop, doop, doom. I can wait forever. Let's start. And the secret JavaScript feature is atomics. Yeah, it's there. You can check specification. Scroll. As you can see, it's there. There are plenty of methods, and they were added in 2017 with ECMAScript 2017. But here, the main question here is not what is the secret API, but why it's secret. It's secret because you cannot use it by default. No, technically you can. You can, as you can see, take the global object atomics, call some methods there, but they don't have any sense. Why? Because atomics was created to work with the parallel code. But here in JavaScript, you don't have parallel code or concurrent code. It's single-threaded, as you know, JavaScript. And all your code is running into single thread. And there is no way how you can create two parallel or concurrent threads or processes that will have access to the same block of memory or object, that they can change it concurrently, and you may run into situations like race condition or deadlocks. And why I'm talking about that? Because there is a small secret. You may say, Vlad, you are wrong, because we can run JavaScript in two parallel processes when we use workers. For example, in Node.js it's thread workers, in browser it's just workers, or service workers, shared workers, different kind of workers. And I'm saying you are right, but the problem here that they don't have access to the same block of memory that you have in browser, for example. The only way how you can communicate with a worker, as you can see, I created a simple worker, communicate and pass the data between those two parallel threads or processes with a post message. And if we pass some object, it will be cloned. It means, like, if I say it here, A, for example, browser will clone this object and say send it there. Browser will clone this object, and if I change any property afterwards, they won't be changed inside the worker. And that's why they have completely separate blocks of memory. In this case, you may say, Vlad, but there is a transferable object. And you can see here what the transferable objects are in JavaScript. And you're completely right. We can transfer buffer array. The browser won't clone them at all, like here, for example. Yeah, I have an example. Like here, browser won't clone them. The buffer, as you can see, it's inside the object. The object itself will be cloned completely, and a worker will have a different copy of this, different reference on different object, but the buffer inside this object, it's passed to as a second parameter. It won't be cloned. Yeah, but here is you have a small trick that when you pass some, the browser will just take the reference to this block of memory, to this buffer array, yeah, just a memory, piece of memory, block of memory, and transfer this link to the worker, where the worker will use this link. But when the browser transfers this link to the worker, it's not cloned, but your main thread loses the link to that block of memory. And it's quite easy to check. As you can see, we have buffer. Yeah, we check the length of this buffer here. Then we just transfer the link to the worker and check the length here. Let's see. Let's update our page and see. As you can see, the first thing we have the full 120 bytes, but after we send, we as a main thread loses the link to this block of memory and we cannot change it. It means this block of memory can be changed only in single thread. It cannot be accessed in parallel. And why we are gonna talk about atomics if they cannot be used in JavaScript at all? There is a small thing. Together with atomics, they presented the way how you can define a block of memory that can be accessed in parallel or concurrently from different workers. For example, you have your main thread and the same block of memory you have access to from the worker, and they both can concurrently change bytes in this block of memory. And it's called SharedArrayBuffer. As you can see, I created a SharedArrayBuffer, and let's see how it works by default. Let's update, see, SharedArrayBuffer array is not defined. Probably I'm lied to. Or not. That's why I've said that it's secret API, because you cannot use it by default. As you can see, you cannot even have an access to it in non-secure environment. As you can see, I printed this global variable, this global window variable, cross-origin isolated, and it says false, because this window is not isolated. To isolate it, you need to apply different headers. If you don't know about them, don't worry, I have video about that. You can check here. Let's see what changed if I add those headers. Okay, I refresh, F12, cross-origin isolated true, and there is no errors. But end script is the same. The changes that I've added are just headers. Our first request, and we see to use SharedArrayBuffer, you need these two headers. Cross-origin opener policy, see here video, and cross-origin embedder policy, see video here. Yeah, and then you can have access to it. Let's play with it. Okay, first of all, let's count to 200 in parallel. As you can see, this is the main thread. Yeah, here we create a worker, and here we create a buffer, SharedArrayBuffer. Let's calculate. We will calculate to 200. That's why we can use integer 32 array, and we send to this buffer with action add. We're starting with a 0, yeah, and every millisecond we will add 1, and this action we will do 100 times. It means this main thread will increase the first byte of this, the first number, sorry, 4 bytes, for this array by 1 every 4 milliseconds, and finish when it reaches the 100. The same we will do in worker. We get this add action, we have access to our SharedArrayBuffer, and the same code. Okay, let's start and see what happens. It's not 200. Okay, let's try to refresh. It's not 200. It's not 200. Why? Simple, because those two threads, threads or process, running in parallel and have access to this block of memory. And even if we do this quite simple operation, just +1, this simple operation consists of two operations. We should read the value from the first cell of this buffer array, add 1, and write back this value. And let's imagine if you have two parallel threads and both of them read the value at the same time. For example, the value is 2. And both of them have the same value too. Both of those parallel threads write the same number, but they should write different numbers, yeah, because each of them should count to 100. And how are we going to solve it? That's why we need atomics. We have atomic, as I showed you, we have a global atomic object that has, for example, method add. And it just adds 1 to the first number in this integer 32 array. Great. And this operation is atomic. It means while this operation is happening, other threads will wait until this operation is finished. And great. Let's change everything to atomic. And let's run the same code right now. F12, 200. 200. 200. As you can see, atomics has multiple methods with this simple methods like add, as you can see, and this is operation with bytes and bits. Exchange, that's for changing. Exchange, compare exchange, we'll talk about later. Load, that's for getting the value from the array. Notify, that's we'll talk about later. Or store, to set the value. Substitute, it's to substitute, and XOR. Yeah, as you can see, those basic methods you can do, and all of them are synchronized between two parallel threads. Okay, let's see a bit different, a bit more complex example. Okay, right now let's take a look at more complex example of using this shared array buffer. And we will use the classic example. We will calculate Fibonacci numbers in parallel in two threads, the main thread and the worker. Great. In this case, as you can see, I created the worker. I created a shared array buffer. Yeah, and I use big int because Fibonacci numbers are big enough that we should use big int. Unfortunately, int is not enough for this. And as you know, that here we cannot, it's not enough to use this atomic operations like add, sub, or and or others. Here it's a bit complex example to calculate the Fibonacci numbers, and you need multiple operations. In this case, I need, for example, read the previous value, read the current value, replace the previous value with the current value, and add to the current value previous value. And we will just calculate like that. As you can see, there are 4 operations. Yeah, each of these operations are atomic, and it's okay to use it in parallel with different worker or thread. But between those operations, they are not atomic. It means I can read here the value from the second element of this array, but it can be changed in a second or in a millisecond by the parallel worker. And when I read this one, the numbers can be different, completely different, and I will sum different numbers, not the previous one and the current one, to get the next number. Yeah, and the same as here. Probably we read this 2 values and try to replace them, but they were already replaced in the parallel worker. It means we cannot guarantee that we'll have the same example. We will have the same mistakes that we saw before. And we need to synchronize all of these operations, all these atomic 4 operations. And it can be done. There is 2 methods called await async and wait, as you can see, that allow us to synchronize the entire shared array buffer. It works like that. It tells, okay, let's check the first element of this array, and if it equals 1, then we should wait. If it's not, we shouldn't wait. We can continue. It means it's not blocked. As you can see, for calculations I use the second and the third element of this array, but for synchronization I use the first one, the first element. And as you can see, like that, we can lock shared array buffer and say, okay, right now we are working with this. And when we did all our operations, we should notify other workers, other parallel workers, to unlock them. How it works, as you can see. The same code I use in my worker. Here, I change the value. If it's equals 0 of the first element, yeah. If it equals 0, I'm changing to 1. Great. After, if the first byte isn't 1, then I can continue. It's not blocked. But if it's 1, we will wait, because it's blocked by another thread. When another thread, for example main thread, finish all its everything that should be finished, it updates the first byte to 0 and notifies other parallel workers that right now wait. We notify all workers that await for the first element of that array is this one, and this one will check, okay, the value is 0, cool, it's not 1, we can continue, and continue to do our job. Great. And like that we can calculate Fibonacci numbers with a simple functions in parallel. As you can see, yeah, we have here logs from the main thread. This is simple for and from Fibonacci worker. Okay, that's it. I hope you enjoyed. See you on GitHub. Boop, boop, boom. Oh, you're still here and not subscribed? Subscribe, click like button, type the comment. That's very helpful. That's for us, for our relationship. I'm creating content for you. You subscribe and like it. That's simple, yeah? Okay, I hope you enjoyed the entire series of 4 videos about CORS, protection, and the secret API. There are plenty more in the future, new formats about creating useless stuff with your JavaScript and phone, creating useful stuff, probably parallel programming in JavaScript and WebAssembly. Yeah, plenty more. I hope you like it. I hope you subscribe to like it. Yeah, it's better to say it like that. Okay, thank you and see you on GitHub.